Hello, everybody. Welcome back. I hope you're having a great day so far. I'm Michael, and I'm back learning and teaching myself Python today. Today is Wednesday, December 18th, and we are in chapter 5 of Data Structures and Algorithms in Python. We've come a long way so far, reading aloud all of this whole textbook and doing the practice problems. We are learning about arrays currently, and yeah, I appreciate you guys joining me and give yourselves a little bit of a pat on the back for also learning a new skill here and studying up. Let's go ahead and let the Discord know that I'm live here. All right. Okay. All right. Let's keep on moving here. Compact arrays in Python. In the introduction to this section, we emphasize that strings are represented using an array of characters, not an array of references. We will refer to this more direct representation as a compact array because a single array is storing the bits that represent the data, the primary data characters in the case of the string. Compact arrays have several advantages. Okay, so we have compact arrays here. Compact arrays have several advantages over referential structures in terms of computing performance. Most significantly, the overall memory usage will be much lower for a compact structure because there's no overhead devoted to explicit storage of the sequence of memory references in addition to the primary data. That is, a referential structure will typically use 64 bits for the memory address stored in the array on top of whatever number of bits are used to represent the object that is considered the element. Also, each Unicode character stored in a compact array within a string typically requires 2 bytes. If each character were stored independently as one character string, each character were stored independently as a one character string, there would be significantly more bytes used. As another case study, suppose we wish to store a sequence of 1 million 64-bit integers. In theory, we might hope to use only 64 million bits. However, we estimate that Python lists will use 4 to 5 times as much memory. Each element of the list will result in a 64-bit memory address being stored in the primary array and an int instance being stored elsewhere in the memory. Python allows you to query the actual number of bytes being used for the memory storage of an object. This is done by using the getSize function of the sys module on our system. The size of a typical int object requires 14 bytes of memory, well beyond the 4 bytes needed for representing the actual 64-bit number. In all, the list will be using 18 bytes per entry rather than the 4 bytes that a compact list of integers would require. Another important advantage to a compact structure for high performance computing is that the primary data are stored consecutively in memory. Note well that this is not the case for a referential structure. That is, even though a list maintains careful ordering of a sequence of memory addresses, where those elements reside in memory is not determined by the list. Because the workings of the cache and memory hierarchies of computers, it is often advantageous to have data stored in memory near other data that might be used in the same computations. Despite the apparent inefficiencies of referential structures, we will generally be content with the convenience of Python's list and tuples in this book. The only place in which we consider alternatives will be in chapter 15, which focuses on the impact of memory usage on data structures and algorithms. Python provides several means for creating compact arrays of various types. Hey Vanch, welcome in. I appreciate you stopping by. Yes, thank you so much for 500. We crossed the mark once again. We dipped down below it today, and then we crossed back over it. So we are officially back over the mark. So I just want to thank all you guys again for the support and for joining me night in and night out here learning. You guys are also learning this too, right? So this is just as much on you guys and as it is on me. Hello Muna, I appreciate you stopping in. How you doing? Hey Gina, how are you doing? Yo, Jeremy, how's it going? I appreciate you coming by this evening. Good to hear from you. How are you doing? How's classes going? You on winter break yet? Ninju, how long have you been learning Python? Yeah, I've been teaching myself for about 6 months now. I have a Bachelor of Science in Human Biology and a minor in Chemistry. I graduated back in 2021, and about 6 months ago I wanted to teach myself Python. I'm a chemist in my profession, so I stream after my 9 to 5 job. And so yeah, I've been learning for about 6 months, but about 3 months pretty heavily. The past 3 months I've really been actually dedicating to really taking this seriously. So uh, a little less than 6 months, I'd say. All right. So we learned about compact arrays. So define in simple terms compact arrays. A compact array is a way to organize data in a memory efficient manner by using only the minimum amount of space needed to store the values. Instead of leaving gaps or unused memory, it keeps the data tightly packed together. For example, imagine you have a list of numbers that can only be 0 or 1. A compact array would store these values in bits, smallest memory unit, instead of using larger units like whole bytes, saving space. This concept is commonly used in programming and data structures to save memory and improve performance. Interesting. Okay. A way to organize efficient manner. I like that definition. Oop, oop. Okay. Is this the only language that interested you? No, I actually was interested in a lot of different languages. I decided to just go down this route because of the Harvard CS50P course was the first ever, you know, hands-on exposure I got with Python and with programming. It was the first ever time I ever seen a line of code in my life. Um, and I have I have a little bit of a theory. I don't want to get too in depth. I talk about it every stream it seems like, but I have a theory that I feel like current CS students that are like in the CS field and also just people maybe teaching themselves. The current trend is to try to acquire as many languages as possible, but are we really grasping the knowledge that and retaining it in a deep level? So I'm mainly focused on mastering a single language such as Python at the moment, in various angles, from machine learning to data structures to algorithms to whatever it takes to be able to then I will expand forward and hopefully it'll be much more of an exponential growth rather than like a slower, it'll be much quicker. They can transition from language to language once I already have a mastery in one. So that's my ideal here. I don't know if it's true. We'll find out. Appreciate you coming in and talking with me, though. Thank you for being here. Okay. Um, Primary support for compact arrays is in a module named array. That module defines a class also named array, providing compact storage for arrays of primitive data types. A portrayal of such an array of integers is shown in Figure 5.10. Figure 5.1 integer stored compactly as elements of a Python array. The public interface for the array class conforms mostly to that of the Python list. However, the constructor for the array class requires a type code as a first parameter, which is a character that designates the type of data that will be stored in the array. As a tangible example, the type code "I" designates an array of signed integers, typically representing at least 16 bits each. We can declare the array shown in Figure 5.10 as primes array I with a list of all the integers. Okay. The type code allows the interpreter to determine precisely how many bits are needed per element of the array. The type code supported by the array module are shown in Fig Table 5.1, are formally based upon the native data types used by the C programming language, the language in which is most widely used distribution of Python is implemented. The precise number of bits for the C data types is system dependent, but typical ranges are shown in the table. So a signed char is 1, an unsigned char is 1, Unicode char. Okay. What is the next language you plan to learn after? I really don't know. I feel like I'm just kind of breaking the surface here and getting past that beginner, more into intermediate realm of Python right now. So I'm kind of really focused on this, and we have a lot of material to get through in terms of book. We got the rest of this DSA, we've got Fluent Python that we're going to read, and we also have Python machine learning that we're going to read. So we have a lot of material to go over still. So yeah. Okay. The array module does not provide support for making compact arrays of user-defined data types. Compact arrays of such structures can be created with the lower level support of the name C module named C types. For more discussion on C types module, okay. Dynamic arrays and amortization. When creating a low-level array in a computer system, the precise size of that array must be explicitly declared in order for the system to properly allocate a consecutive piece of memory for its storage. For example, figure 5.11 displays an array of 12 bytes that might be stored in memory for locations 2146 through 2157. So 12 bytes, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 12 bytes of memory that are saved in a compact array in memory, which means that they're just in a sequence here with no gaps, right? An array of 12 bytes allocated in memory locations. Cool. Because the system might dedicate neighboring memory locations to store other data, the capacity of an array cannot trivially be increased by expanding into subsequent cells. In the context of representing a Python tuple or stir instance, this constraint is no problem. Instances of those classes are immutable, so the correct size of an underlying array can be fixed for the object is instantiated. Okay, so if we created an array with that was a tuple or stir instance, we can't expand that array and add onto it. It's immutable, right? So I mean, you can concatenate two stirs together, but okay. Python's list class represents a more interesting abstraction. Although a list has a particular length when constructed, the class allows us to add elements to the list with no apparent limit of the overall capacity to the list. Yeah, exactly. So I guess tuples and stirs we can't, add, they're immutable, right? We can't physically go in and modify individual indices of a stir and override them. Same with the tuple, got you. But with the list we can, right? Although a list has a particular length when constructed, the class allows us to add elements to the list with no apparent limit on the overall capacity of the list. To provide this abstraction, Python relies on an algorithmic sleight of hand known as a dynamic array. Okay. The first key to providing the semantics of a dynamic array is that a list instance maintains an underlying array that often has greater capacity than the current length of the list. The first key to providing the semantics of a dynamic array is that a list instance maintains an underlying array that often has greater capacity than the current length of the list. Okay, so what Python does is when we call a list instance, it makes a dynamic array in memory, I guess, that is larger than our list instance to save room just in case. Okay. For example, while the user may have created a list of 5 elements, the system may have reserved an underlying array capable of storing 8 object references rather than only 5. This capacity makes it easy to append a new element to the list by using the next available cell of the array. Okay, if a user continues to append elements to a list, any reserved capacity will eventually be exhausted. In that case, the class requests a new, larger array from the system and initializes a new array so its prefix matches that of the existing smaller array. At that point in time, the old array is no longer needed, so it is reclaimed by the system. Intuitively, the strategy is much like that of the hermit crab, which moves into a larger shell when it outgrows the previous one. Gotcha. So dynamic array, when a list instance is created, Python also creates a quote dynamic array in the system memory, which which is slightly which saves additional space for the list to grow / append elements into. Okay. When the space is extra space is exhausted, right? Python calls the system to reserve a new, larger dynamic array, moving the elements, or not dynamic array, saving it as the same variable name, right? A new array, so its prefix matches that of the existing smaller array, saving it as the same saving it much more a larger dynamic array, saving it as the same prefix original elements, discarding the original and continuing with the new. Okay, so I'm going to ask Jipity to clean this up a little bit. Can you clean up this? All right, we got some comments here. Thanks so much, guys. Chattington, elucidate the implications of tail call optimization recursive algorithm. Construct a Python function to compute the Fibonacci sequence using recursion and then refactor it to demonstrate manual. I'm not. Are you asking me to do that? I don't know what you're asking, but welcome. Omid, thank you so much for coming. You seem to be much more disciplined into teaching yourself coding. I can only do 5 minutes before I stop, and that's basic web dev. Maybe I just hate coding. No, I just don't. I definitely. I just. I don't know. I don't beat yourself up. It's easy to try to, make comparisons, and it's easy to, especially online and stuff. But just try to take things at your own pace. I think it's unfair to set expectations or predetermined expectations for yourself when doing this. So if you go into it thinking like whatever happens, whatever I learn, great. I don't care. I'm just going to take these 2 hours, whatever I get out of it, I don't care, right? Stop thinking of it as like an investment, right? It must be like an investment. So like if you're treating it as an investment, you're hoping to gain something out of it when in reality you might not gain anything out of it. So just I think just limit expectations might be easiest. Yeah, Chattington, we already moved past recursion. Chapter 4 was recursion. We completed quite a few Chapter 4 practice problems in recursion. I think already did the Fibonacci one and stuff for his examples and everything. We computed powers, converts, summing sequences, all that jazz. So right now we're moving on to data structures in Chapter 5. So thank you for stopping in. Quinn Riley, ChatGPT is my daddy when it comes to learning coding. Yeah, I like to use it too, but I like to you have to use it responsibly, of course. I often will say I don't like to have it show me any code really. I like to take it from words and deduce the words into my program rather than I think that if you can translate the words into programming, I think that goes a lot further in your studying. Um, we seem to have a lot of new people. So for those that are new, my name is Michael. I graduated college back in 2021 from a state school. I graduated with a Bachelor of Science in Human Biology and a minor in chemistry. I was a undergraduate teaching fellow for the chemistry department at my school. I taught the undergraduate general chemistry labs for as an undergraduate. I even administered the labs solo, with the graduate students. I got a job as a formulation chemist right out of college, where I have uh, really enjoyed myself. But I've also wanted to further expand my knowledge and skill set into different areas, maybe bioinformatics, biocomputation, whatever, or even just into programming, other programming areas in general. So I know it's just not trying to. There's nothing to really to gain out of this, but obviously to improve myself on a personal level and on an educational standpoint, and just get better, and obviously create an environment with you guys if anyone else is in a similar situation. I often feel that the current CS environment is fairly and very competitive, and oftentimes feels that it's something that you have to seek monetary value out of, or um, that seems like the end goal, when in reality I just want to learn this to get better on a personal level, as just a goal of just continuing education, right? And I wanted to see how far I could get on a solo, if I didn't have to go back to school or whatnot, reading textbooks and using you guys and everything. So if you guys are interested in this, I've been coding for about 6 months. I've created a few projects. I completed Harvard CS50P. I completed a final project in that where it was an inventory chemical system storage system. I recently released a task tracker application to my GitHub, which use date time module to track tasks over the course of days, reducing those attributes for accordingly as the due dates got closer, and it was more object oriented. And currently we're reading the data structures and algorithms book, and then in the second half of my streams I work on independent projects like the task tracker app. But now we're making a project called the Small Business Manager, which takes in inventory items similar to my projects in the past, but we're now going to process these items into transactions as sold items or for sale items, and then provide the user with the ability to create like expense reports, income statements, general business needs that small users and business owners might not know how to formulate themselves or might not care to do. And so we have a program to do it on the back end. So we've been working on this for about a few weeks, just on and off, very casually, and it's been a lot of fun. So yeah, in the first half, like I said, I do new learning, and then in the back half we try to implement that learning into projects. All right. You just need to find what you like. Definitely. I mean, try to find out different things. I tried web dev and found it was way harder and more boring. What do you mean by different things? What program link? Mike said, "Hey, I like your name." uh, what programming language are you familiar with? Just Python mainly. I did complete half of the Odin project online, but I found that I shifted back into Python because I just wanted to continue developing a mastery in one single language before I expanded out into others. I really thought that that would be more beneficial than trying to collect languages like Pokemon in the Pokedex, right? Or like gym badges. No, I've never done any C++ or C Sharp. No. If you guys want access to my notes, all of my notes are on my GitHub. I push all of these notes to GitHub for this current book I'm reading, Data Structures and Algorithms in Python. I also provide I've created Discord for a compilation of all my study resources. And so it's just linked below. It's completely free. So if you want access to PDFs that I'm using, these books or the notes or anything else that I provide on the streams, it's all there. So join that if you guys are interested. What you're doing is really cool. I really appreciate that. So kind, and thank you so much for stopping in. And I appreciate all the support you guys have been. Um, have you tried doing this without AI? Yeah, I only use AI very responsibly. I use it to break certain topics of the book down, but I never copy code. I never even try to have the AI show me code unless I really can't figure something out or I'm learning something new. but I will always preface that to not show me code, and that's something that I've been preaching, and that's been helping me a lot. I mean, obviously, we have our little thing loaded up to explain a little bit better, more in depth on these more challenging and more jargony concepts, but we use it very responsibly, and I try to emphasize to you guys that to use it this way as well. To if you're learning, because copy and pasting really does nothing. Okay, so when a list is created, I had it revise my little notes here. When a list is created in Python, it has dynamic array. All right, I will take this though because this is my notes just revised. I wanted to make it less wordy. When a list is created in Python, it allocates a dynamic array in the system's memory, reserving extra space to allow for the list to grow as elements are appended. Once this extra space is fully used, Python requests the system to allocate a larger dynamic array. The existing elements are copied into the new array, and the old one is discarded, allowing the list to continue to grow seamlessly. Exactly, that's exactly what we said here, just a little bit more streamlined. Awesome. All right. I appreciate all you guys joining me. The channel's been growing really fast. I've been getting a ton of support and feedback. I really just wanted to provide a beginner's perspective to learning this. I found that everyone that was streaming or making videos was either very experienced or just are also in college themselves learning it on a higher level. And there was really no one that was coming at this from ground zero. So I wanted to bring that to the table, and in case there was anybody else that was interested in this. So you use it as a mentor and not to look at code. Exactly. I really try to use it as if it was a physical teacher person right here, like looking over my shoulder. I have it. That's exactly how I use it. I don't use it to show me any lines of code. I really try to not. Obviously, sometimes it does show me some stuff without me asking it to, but we try to skip over it. Okay, let's keep going here. So we know that we have this hermit crab kind of method where in memory we create a compact array where we allocate a certain amount of space needed. Well, that's just a compact array is just the minimum amount of space needed to store value. So that wouldn't be a dynamic array. A dynamic array is in memory was a consecutive piece of memory where it leaves a little bit of extra space for us to actually add or append elements into our lists. Elements or list instances. So and then if we need to grow, it will just replace it with another place in memory, essentially, from what I'm understanding. Okay. I'm talking a lot. I'm running out of breath. Hey, quick question. I'm a professor of development. Awesome, cool. Thanks so much for joining. I use Copilot to help me teach where I'm errors coming from. I don't think using AI is a problem. Yeah, definitely not a problem at all. I oftentimes I think it's really useful if I get an error, I'll throw the error just into it, and it'll tell me like you give me more because that cryptic language is hard to deduce. Oftentimes when I'm working in the terminal, I'll use AI, but I really try on the coding aspect and the learning is I really try not to have it show me code. I'll provide it my code, my attempt first, and say, okay, where am I going wrong here in words, and then it'll tell me how I can change things. So you have to preface it and prompt, wisely. Is this a book from No Starch Press? No. So on my channel, Isaac, if you're interested, I read all of Python Crash Course Live, which is from, I think, No Starch Press. I read all of this live when I was learning Python initially after CS50P. I felt that this book really, really well went hand in hand with CS50P, and it just really helped solidify those concepts that the course kind of skipped over really lightly and didn't really go too much into detail. But no, this one is a more advanced, not advanced, it is more advanced than obviously Python Crash Course, but it's getting into that more intermediate, learning how to get into the actual more computer interaction with Python and system stuff. And so data structures and algorithms. Marty, only thing I know is how to print hello world. I was just like that. I'd never seen a line of code before. I didn't even know what hello world was. It was the first time I ever heard it was when I watched CS50P. I swear, I had never even heard that line before. And so it just goes to show you that we're growing here, and I wanted to show you, you take that as an example, right? All right, let's continue in here. Um, we give empirical evidence that Python's list class is based on a strategy. The source code for our experiment is displayed in code fragment 5.1, and a sample output of the program is given in code fragment 5.2. We rely on a function named getSizeOf that is available in the sys module. This function reports, what's going on here? Reports the number of bytes that are being used to store an object in Python. For a list, it reports the number of bytes devoted to the array and other instance variables of the list, but not any space devoted to elements referenced by the list. Okay, so we import sys. We have a data list right here. We say for k in range of n, a equals the length of data, b equals get size of data. So we're just getting the size of the length of the list for each element, not the element itself, but as the list grows, we're seeing how the list grows. So we see that we kind of reach some caps here. We have some bounds, the dynamic, okay, so this is the dynamic, we can see it happening here. So an initial length 0 holds an array of 72 bytes, right? As we add elements in there, it looks like we can add up to 72. Once we add in 1, we go up, we have a new dynamic array created at 104. And so that can house 4 elements. Once we get past 4 elements, we have to open up a new dynamic array for 136. And then we open up a new dynamic array that holds 200, and then 272, and then finally 235. And so I bet it continues to go on and on. I love that hat, man. Where'd you get it? Honestly, I got it at a thrift store. Like it was like I think it was just homemade, like by people. They had a bucket of them, and they were like $1 a piece. So I grabbed like 5. I love the Christmas lights in the back. Yeah, I got a lava lamp. Let's shake it up. Let's get the lava lamp shook up here. Okay, it's not totally melted yet. We got to get it melted. All right. It's not looking that pretty yet, but it'll get there. It'll get there. Okay. In the evaluation of the results of the experiment, we draw attention to the first line from code fragment 5.2. We see that an empty list instance already requires a certain number of bytes of memory, 72 on our system. In fact, each object in Python maintains some state, for example, a reference to denote the class to which it belongs. Although we cannot directly access private instance variables for a list, we can speculate that in some form it maintains state in the state information akin to and the number of actual elements currently stored in the list. Underscore capacity is the maximum number of elements that can be stored in the currently allocated array. And underscore big A is the reference to the currently allocated array, initially none. Where is it? Where are these at? Where's underscore n at? What's it showing me underscore n? Although we cannot directly access private instance variables of a list, we can speculate that in some form it maintains a state of information akin to is this like a sum? What does this mean? This explanation is about how Python list object manages its internal data. Let's break it down. Private instance variables. Python's lists have internal variables that handle their operations, but these are private, meaning they are hidden from direct access to prevent tampering. Yeah. State information speculation. While we cannot access these private variables, we can make educated guesses about the list. Oh, okay, so these are instance variables that are not accessible because they're denoted by the underscore ahead of them, right? So these are self dot underscore n, which is okay, got you. 1K Flash. Hey, welcome. I appreciate you jumping in and leaving a message. Is this a college course? How do you teach yourself and develop an actual understanding of it without tests, projects, or exams? Do you find it more difficult to understand what you're reading? Um, yeah, I can give my feedback on this. I'll take everything what I say with a grain of salt, guys. I often like to say that I like to treat this as a peer-to-peer relationship. You and I are in class together learning this. This is like if we were in a lecture hall learning together. I am a peer with you learning this. So don't, this is not a teacher, a student dynamic at any, by any means. I am a learner, I'm a beginner, and so I just wanted to show what it's like as a beginner so other people could also maybe follow along with the same perspective. So um, I really it does take a lot of discipline, I will say. Now, the once you start developing the habit after over time, you will start to see that desire to continually go and go and go. But at the start, it is very hard. I'm not going to preface, I'm not going to sugarcoat things. It is very hard to force yourself to sit down and learn something that you have no idea about, especially if there's no one else there and there's no one else, no teacher there, and there's no final exam pressuring you, there's no grade. But I created this channel, right, as a way for us to come together every evening as like a study group and like, learn together and go through these problems together. Because like you're saying is, and like you're demonstrating and telling me is, a lot of other people out there struggle maybe with staying disciplined and but they want to learn these things, and they maybe don't have the financial means to pay for some courses or go back to school. They have to work. Exactly. I work too. I work a 9 to 5 and I do this after work every day. And so I created the stream as a way to hold not only myself accountable, but provide an environment for other people to sit down and in the background listen to the topics. And oh wow, I learned something today while I was doing something else. Or if you're following along 100%, then you're getting like all of it out of it. But it's as much as you put into it. But I created the stream as a tool, so this helps me a lot. I created the Discord link below, which conglomerates all of my study resources into one area. It it is I really tried to set it up like a roadmap for you guys to follow exactly what I would have done so far. I have kind of weeded through the mud and picked through the weeds about what stuff is good for Python and what stuff I kind of stayed away from. And so I read all of Python Crash Course, did CS50P. It was great at solidifying those concepts. I did all of the try it yourself practice problems live, just like I'm doing the in-course problems here. It's just, you really have to force yourself to do things sometimes that you don't want to do. And eventually you might end up liking it. And, in my circumstance, I did want to do this. I had a desire, and obviously in the stream has just ramped that up. You guys have been showing me a lot of support and so much, love, and it's just been great. You guys have been, I've been growing. This channel is going crazy. It's just amazing. I can't believe it. So, anyways, sorry for the ramble. I ramble on a lot. Um, and definitely, you do need. I will say, this would be a lot harder without using AI to help break down these concepts. I will preface, you need to use it responsibly, to not show you code, to not show you how to do things, but to explain things to you. And if you need it to look at your code, you need to try it yourself and then provide your attempt to it rather than it just coming up with the answer for itself. You need to have it tailored to your education and your learning, and you need to prompt it as so. Um, Coding is so hard for me, low key. It is really hard for me too. I struggle through it, but I will say I'm a lot better than I was 2 months ago. I'm a lot better than I was a week ago. So every day you can get a little bit better, and over time you'll see that it's a drastic improvement. It just takes a little bit of time, and once you look back in hindsight, you'll see, wow, I actually did improve a lot. Before I couldn't even print Hello World. Now I wrote a whole task tracker application that does reading and writing files, right? Like it's crazy. Like it just little by little, day by day. Where is this book from? I've also finished Python Crash Course um, Part 3 and have been looking for a book teaching data structure and algorithms in Python. Have you any recommend? Yeah, Isaac, this is DSA in Python. I just kind of browsed, filtered through some Reddit forums and did some, research on some various books, and I found that this one was on. I found a PDF of this one, and it seemed I had it had practice problems that I really like that I was looking for. I needed a book with practice problems. I needed a book with example code, to show me and tailored to Python specifically. And so this book has all of that. It has example codes. It has the algorithms. It has walks you through it. It is jargony. It is hard. You do need to maybe use AI to simple it up a little bit. But that's just with the technicality of programming itself. Your energy and empathy is on point. Awesome. That's what I want to bring to you guys. I want to show you guys that this is supposed to be fun. Take the pressure off this. It's not supposed to be something that don't if it's something that you're forcing yourself to do because you need a job or you're gonna maybe burn out at the end of the day. If you treat it as a hobby, as a passion, it'll go much farther with anything in that matter. Exactly, 1K Flash. We're learning together. Exactly. Angela, welcome. I appreciate you coming in. How do you retain the information you learn? Lots of practice. So all these books have practice problems, and I don't skip over them, right? In chapter 4 didn't have too many reinforcements. I only do the reinforcement problems because it gets a little bit redundant after into some of the other ones, and the other ones are pretty lengthy, more like projects and technical theoretical stuff. But the reinforcement ones give you a lot of practice, and as you can see in chapter 3, we did 34 practice problems live on stream consecutive, like not day after day. So we really grinded, big O notation and functions and time complexity functions, and really had to grind that just through repetition. And so raw repetition, you guys, is a real factor when it comes to personal learning. So don't count out just raw repetition over and over again. I only am using just Markdown to take my notes currently. I was using TXT in chapter 3, but someone told me suggested that I use Markdown, and so we used Markdown for chapter 4, and I'll show you that here. Chapter 4 notes for recursion, and I do Shift Option View, or is it Shift Command V? Yeah, Shift Command V. We have a nice. You can get all these notes on my GitHub, you guys. I have all of my personal notes on and all these practice problem solutions that I've been doing, my solutions, um, all on my GitHub, all in this shared repo, DSA-Pi, linked down below. Also, I have a Discord link below for all my study resources, PDFs, everything, and a community just to come together and we can talk offline and keep learning. Okay, so dynamic arrays, I feel pretty good about this. Dynamic arrays don't seem that bad. A array module does not support for making compact users. Compact arrays can be created with lower level support of C types. Okay. 5.3. Okay, 5.3 is about dynamic arrays and amortization. And amortization. Okay. When creating a low-level array in a computer system, the precise size of that array must be explicitly declared in order of the system to properly allocate a consecutive piece of memory for the storage. Okay, well, what the heck? When creating a low-level array, the precise size of the array must be explicitly declared. Okay, for low levels in memory, exactly. We're not using dynamic arrays for low-level arrays. Those are using compact arrays, right? For example, figure 5.11 displays an array of 12 bytes that might be stored in memories 2146 and 2157, these bytes. Okay, an array of 12 bytes allocated in memory locations, right, gotcha, let's wait over that. Because the system might dedicate neighboring memory locations to store other data, the capacity of an array cannot trivially be increased by expanding into subsequent cells. In the context of representing a Python... Wait, we already read this. What's going on here? We already read this. Right? Yeah, we already read this. sorry guys. Okay, here we go. So yeah, we were right here. These are the these are protected or hidden instance variables associated with the list objects, right? So as soon as the first element is inserted into the list, we detect a change in the underlying size of the structure. In particular, we see the number of bytes jump from 72 to 104. So when we have a length 0, meaning empty list, we reserve 72 bytes in length for just a blank list. But as we add an element, we jump up to 104. Okay? An increase of exactly 32 bytes. Our experiment was run on a 64-bit architecture machine, meaning that each memory address is a 64-bit number, 8 bytes. We speculate that the increase of 32 bytes reflects the allocation of an underlying array capable of storing 4 object references. Okay, so if each memory allocation is 8 bytes, and we went up 32 bytes in our memory allocation for this array, we know that we can store 4 objects in this list. 4 times 8 is 32? Yeah. Okay. Okay. Yeah, this hypothesis is consistent with the fact that we do not see any underlying change in the memory usage after inserting the second, third, or fourth element in the list. Exactly. We have a dynamic array that can now house 4 more elements. So we say 104, we get all 4 of those. Now we have to shift to a new dynamic array at 136, going up another 32. Okay. So here, though, we went up, is it double 32? Yeah, it would be double 32. We went up 64 bits here for this size, and then we went up 72 bits for this size. Okay. All right. After the 5th element has been added to the list, we see the memory usage jump from 104 bytes to 136. We have assumed the original base usage of 72 bytes for the list. The total of 36 suggests an additional 64 bits, exactly, up to 8 object references. Again, this is consistent with the experiment as Python memory usage does not increase again until the 9th insertion. At that point, 200 bytes can be viewed as the original 72 plus an additional 128 byte array store 16 object references. The 17th insertion pushes the overall memory usage to 272, hence enough to store 25 element references. Because a list is a referential structure, the result of the getSize function of a list instance only includes the size of representing its primary structure. It does not account for the memory used by the objects that are the elements of the list. In our experiment, we repeatedly append none to the list because we do not care about the contents, but we could append any object without affecting the number of bytes of the getSize data. Okay, so what this is saying, guys, is as we add elements to our list, our list dynamically increase in memory, right? As we increase to 1, we pre-reserve an addition of 4 places. So as we continually adding, as you see, we jump at this point 5, we reserve another 4 places, and at this point 9, we reserve 8 places, and at this point 7, we reserve another 8 places. Or we reserve 1, 2, 3, 4, 5, 6, 7, 8, 9 places. 9 places, right? 8, okay, yeah. So, but what's interesting is this is not because of the individual objects in our array have that size. No, 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 no. This is just because the array itself is getting larger in memory, so we have to house references to those objects in the array. But the objects have their own memories associated elsewhere, which are referenced using random access memory, right? Crypto, the only way to retain information is to continually do it. So you really just got to practice and then eventually it sticks in your brain, but you can't just memorize it on the spot. Exactly. Markdown works with Obsidian. I'm going to join your Discord. I'd love to hear about your development journey more. You're using this technology in the best way I've seen. Keep teaching. Awesome. Thank you. That's so kind. And that's a lot of feedback, and I appreciate, that was really nice. Lambda, hey, appreciate it. Welcome back. Uh, Cubify, how you doing? Did you manage to resolve that recursion problem yesterday? Yeah, we solved 4.8. So we solved it two ways. We solved it initially using a while loop. It took us forever. We got a lot of help from Chase and Space. Shout out to Chase and Chat and everybody else. And then we also solved it using we swapped the for loop and put our base case at the top and solved it this way as well. But this one was by far the hardest one we've done so far. Um, this one was also pretty hard because it had us think about things. We had to track magnitudes of as we, recurse down through our string. We had to track the magnitude and converting string to integers without using the actual, without calling like without cheating it out. So we solved it, but it was it took us forever. I felt real defeated afterwards, but we live and we learn, and we're moving on, and yeah. Okay. Um, because a list is a referential structure, the get size function. Okay, got you. So we'll say this. We'll say um, I want to say um, as the list grows in size, lists are referential to the objects in size. Lists house references to the objects inside them. Inside. The physical memory of the objects is not of the individual is not applied to the list the list's memory size. The objects are accessed elsewhere in memory. Gotcha. Are housed elsewhere. Gotcha. Cool. Um, hey Barlocks, we appreciate you coming in. We. Yes, I am taking notes. I have all these notes available as well as I do all of the reinforcement problems at the end of the chapters, all of my personal solutions, all on a accessible GitHub repo, linked down below. Yeah. How do you live stream? I just use OBS, just my MacBook Pro. I have a MacBook M3 Pro, MacBook Pro M3 Pro, got last year, or at the beginning of 2024. To really, push myself to learn. I figured if I made a big purchase like that, I had to learn. So I went for it. Okay. 5.3.1, implementing a dynamic array. Although the Python list class provides a highly optimized implementation of the dynamic arrays upon which we rely on for the remainder of this book, it is instructive to see how such a class might be implemented. The key is to provide means to grow the array A that stores the elements of the list. Of course, we cannot actually grow that array as its capacity is fixed. If an element is appended to a list at a time when the underlying array is full, we perform the following steps. Allocate a new array B with larger capacity. We set all the values at B at index I equal to the value of A of that index for all the values I to 0, right? Exactly kind of like what we did in this function here, but we were multiplying it by 2 each time. Okay, gotcha. Cool. So we set A to B, and we henceforth use A, B as the array supporting the list. So it's pretty much almost exactly like this function, except we're not multiplying the list by 2 and summing. We're increasing the list and creating b. We wouldn't be using m, which is the floor divider of 2. Using a logarithmic division on or logarithmic function on this sum sequence. We would be creating b larger for an m value that is larger than the length of a, right? So we'd be doing n plus 5 or n times some factor, and we create the b based on that factor. We'd probably use the ceiling of something, right? Cool. So an illustration of this process is shown. So we have an original array A with all of these elements in it at these places. We run out of space because we now have no more ability to add into more cells. So we need to dynamically create a new array in memory. So we we create list B, which has obviously the space capacity to hold the original list and more. We go ahead and make references to those elements that were in A, and then continue forward and remove the previous array in memory. Got you. The remaining issue is to consider how large of a new array to create. Exactly. We need some factor, kind of like in this right here. This factor is a logarithmic division of 2, so we're dividing our array by 2 every time and creating a new one. We need some factor, though, on the inverse side of this function to create an array that's larger. So a commonly used rule for the new array is to have twice the capacity of the existing array that has just been filled. So we would be m is equal to n times 2, right? In section 5.3.2, we will be providing a mathematical analysis to justify such a choice. For those that might not know what this syntax means, floor division just means that when we divide this number, whatever it is in the decimal form, we always will round it down to the nearest whole integer. So if we got like 1.5, although 0.5 rounds up technically in algebra up to the nearest to up, but floor specifies that we want to bring this down. So if we had a sequence of an uneven length, then we would floor it. The floor would obviously take effect there. We have a half for reducing by 2, so it would be rounded down to its most whole integer value. But yes, not as in react and reductions. React and redux, the easy stuff. Sounds pretty intense. Hey, Bilal, I appreciate you coming in. I'm not sure if that's English or not. I only know English, and I guess I could say I know a little bit of Python now. Well, at the very least, you know what to expect when you're faced with for another recursion problem. Yeah, exactly. Hey, Tim, I appreciate you coming in. Thanks for stopping by. What do you think about mind mapping? What is mind mapping? I have no opinion on it because I've never even heard of it, so I don't even know if I might do it just naturally. If it's a study technique, I'm not sure. I hope you keep going. I'll be here for the rest of the chapters. Just found this channel. Awesome, Kai. Thank you so much. I appreciate you so much for stopping in, and I'm so happy that YouTube put you in the right place. It seems like we've been finding a lot of the people that we've been gathering and bringing in a lot of people of or the right audience, we'll say. So bad at talking sometimes. Okay. In Code Fragment 5.3, we offer a concrete implementation for dynamic arrays in Python. Our dynamic array class is designed using ideas described in the section. While consistent with the interface of a Python list class, we provide only limited functionality in the form of the append method, and accessors the dunder length method and the dunder get item method. Remember, so if we want to have a a class object or whatever that is iterable and mutable, we have to have a get item method and a length method associated with that class. That was from chapter 1 or chapter 2. Support for creating low-level arrays is provided by a module named ctypes. Because we do not typically use such low-level structure in the remainder of this book, we omit a detailed explanation of the ctypes module. Instead, we wrap the necessary command for declaring the raw array within a private utility method dunder make array. The hallmark expansion procedure is performed in our non-public under resize method. Okay, so we'll see that here. So we have some import C types, provides low-level arrays. So what are low-level arrays? A low-level array are fundamental data structures that directly interact with the computer's memory and provide a way to store and access a sequence of elements of the same data type efficiently. These arrays operate close to the hardware level, making them powerful but requiring careful management of resources. Characters of low-level arrays. Fixed size. Okay, so where did we talk about low? Here we go. The fixed size. So I'm gonna make a lane thing here and go low-level arrays. Have a 1, a fixed size. They have 2, a contiguous memory allocation, and 3, homogeneous elements. 4, manual memory management. 5, efficient access. 6, lack of built-in safety. Okay. So the fixed size, the size of the array is typically defined when it's created and cannot be changed dynamically. Perfect. I like that definition. Contiguous memory allocation. Elements are stored in consecutive memory locations, allowing for fast access using an index. Perfect. Sounds great. We'll look like that and like that. Okay. Homogeneous elements. All elements in the array must be the same data type, such as integers or characters. Okay, that's interesting. So we have to have all like element data types. Manual memory management. In languages like C or C++, developers must manually allocate and deallocate the memory for arrays. Interesting. I bet that is tricky. I bet that is hard. My C++ people in here and C users, what does that kind of look like? How does that go about? Efficient access. Because of their I hate this word. Contiguous memory layout, accessing elements via an index is very fast, constant time. Perfect. Lack of built-in safety states that many low-level arrays do not perform bounding checks, meaning accessing elements outside of the allocated range can lead to undefined behavior or memory corruption. That's useful as well. Okay. Where are you learning Python from? Sorry, just joined. Yeah, no worries. For those that are new, I'm sorry. I just like to catch up the people that stop in and make sure everyone's on the same page. So if I repeat myself a few times, just bear with me. I'm sorry, guys. It's just kind of how part of the stream is in learning. So for those that are new, my name is Michael. I have a degree back in 2021. I graduated in a degree in human biology and a minor in chemistry. I was very heavily involved in the chemistry department. I worked as an undergraduate teaching fellow for general chemistry. I worked as the lab instructor for general chemistry. And I quickly got a job right out of school as a formulation chemist for a biotech company where I'm currently a scientist too. And I've just found a lot of desire to continue my education. And I think that, computer science and programming would fit hand in hand with my current skill set, and also provide me the ability to further expand my skill set into new fields and areas. And so, yeah, I really am enjoying this. I don't have a super math heavy background. The highest math I went up to was for 3,000 level statistics for scientists. It was required for my major. Also, I did calculus my freshman year of college, but it's been a lot. So if you think that I know a lot of math, or you're inferring that I know a lot of math because of this and it's helping that, no. I've been having to refresh all of my memory on these math operations and everything. And so, yeah, it's been a challenge, but it's been fun. And I started off about 6 months ago with Harvard CS50P. I had never seen a line of code before in my life. I'd never even heard of what Hello World or seen what that line before. I didn't even know it existed. I uh, took that course. It was very challenging. I got lost a lot. I took it over 3 months. I did it the free version online. I did not pay for the certificate at the end. It gets the same amount of material, the same everything is the same except for a paid certificate versus a free certificate, and doesn't really provide you that much value besides the actual Python itself. So I would say if you're thinking about doing that, just go with the free one for sure. Um, I, uh, I would like to provide, I'm thinking about how I could provide, help with CS50P, like providing maybe the solutions to my problem sets that I did in that course, and then maybe my final project, but it would have to be more of an exclusive thing. I know that they're pretty stingent on what you can and can't share, but I think it is pretty important and it could provide a lot of use for, beginners who are lost in that course because they say it's for beginners, but it does move fairly fast. I know you can always just rewind, right? But it is dense, right? And so it's a lot of material you got to learn all at once. And so I think I might make private videos going over those solutions and provide them to the Discord, just so that it's not accessible really by like public YouTube users, and so we don't get flagged for anything. So but if you guys are interested in that, let me know. I can make those types of videos. But I paired that course with Python Crash Course, where I started this stream and started this channel and read all of Python Crash Course live on stream, just like we're doing with data structures and algorithms here. So we're leveling up our game and little by little, day by day. And this book was really, really good in solidifying those beginner concepts and really showing you examples, walking you through the examples line by line. Stuff that the CS50P course kind of had gaps in. This filled them perfectly. Um, I'm making solution videos on my channel of the try it yourself problems. So I'm just going back through and just providing those to beginners like myself, who were in a similar situation to myself, and then eventually we'll dive into. We're doing DSA in Python right now, as you can see on my screen, but we have Fluent Python right here, and then we have Python machine learning. So we have a lot of subject matter we're going to get to. We're going to over the course of this next few months to year, we're going to be learning a lot, growing this channel, growing the community together, all of us together, doing this as one. So yeah, hopefully that's my spiel, guys. So sorry if you've heard that a million times. What days / times you normally stream? Yeah, I'm really, really passionate about this right now. I don't have a lot of hobbies. This kind of is my hobby. I play guitar and do this and walk my dog and go to work pretty much. So, I I I stream every day after my 9 to 5 job as a chemist, from about 7 p.m. to about 9:30, sometimes 10:30, sometimes 11 if I'm really going. But then on the weekends, I'll stream also sometimes twice a day, for about anywhere from 4 to 6 to 7 hours on the weekends daily. So I'm putting in a lot of hours, and we are definitely learning a lot and growing quite rapidly. I've been getting a lot of feedback from people watching, saying like, "Wow, I stopped. I was here a week ago, and I just checked back in, and you've already like doing a lot more advanced stuff." And so it's just going to prove that this learning and this time we're putting in is working here. So yeah. Hey, Mike P. Funk, welcome back. How you doing? Appreciate you stopping in this evening. Okay, so we have this, provides low-level arrays. Okay, got you. So the C types data modules are how you get low-level arrays, because the dynamic array is a subsequent of the list class that we have, right? So they're creating a dynamic array. They're initializing it. They're setting the length of the array to 0. They're setting the capacity to 1, the default capacity, or this is the actual elements, the number of elements, I'm sorry. So it has 0 elements, a default capacity to start of 1, and then we are calling a recursion on this array. No, we have self._make array. We're calling a class method. No, it's not a class method. It's just a non-public utility. to actually make the array based on this capacity. Okay, so this make array, what it does is returns, okay, this calls the actual C type. So this just physically creates the array by the some constant times some constant value. Got you. Cool. And then the constant given is the capacity. So we make an array with a capacity of 1 that is given by the C type. So remember guys, the C types module here is just giving us low level arrays which have fixed size, continuous memory allocation, homogeneous elements, memory allocation, efficiency, right? These are like on board to the system's memory here, sounds like. Okay, we initialize that, we take a length, right? We return the actual amount of elements that are in there as the length. Cool. For our get item, we raise an index error, or so we return the index. So now we can actually index and get items. So now we are both iterable and indexable, right, via length and get item. We can append items, so we can add them to the end of the list. So we have a condition here saying that if we are at capacity with n, so if n is equal to capacity, we call resize, and we call it for 2 size of the capacity. Okay, so resize will call the make array function to make that double size array. Okay, and then also we'll save those elements that were previously in our array in the new array, and then swap the arrays basically. Cool. So very similar function kind of going on. We have like a recursive, very similar function going on to like our sum sequence almost, but just a different kind of process. It's like an inverse process almost, not summing sequences, but creating larger arrays. We're reducing arrays by half, and this one we're multiplying, doubling arrays each time, right? Homogeneous in terms of like chemistry, for me, homogeneous just means all like in the same state. So based on the definition it provided in here, which is similar to the homogeneous definition I have in chemistry, is that they're all of the same data type would be homogeneous. The memory allocation was also a factor of contiguous memory allocation. Yeah, homogeneous of all the same data type. That's what homogeneous means. So think of like a solution, right? If it's clear of particles, it's homogeneous. But if it has individual specks, right, it's not completely mixed. It's heterogeneous. Mentioned programming. So I have a definition here of homogeneous element for programming given by the GPD of array must be the same data type. Contiguous, yeah. Got you. That's another statistic for it, or a definition, right? Perfect. All right, so all this array, if this is kind of challenging, I advise you guys to take this line by line using the chapter 2 of this book. It goes over all these Dunder methods that are needed, right? It goes over the fact that we need a length and a get item to make things indexable and both indexable and iterable. And so we also have these other functions for actually adding and resizing and everything. So this array is just kind of mimicking our class function in a sense, but using the system parameters of saving memory allocations, right? Okay. Where do you get notes like? Where did you get that notes? All these notes are my custom notes. I write these notes and make them myself. So if you want access to these, I have a link down below, which is my GitHub, and I share a repo which you can copy and see all of my notes and all my code solutions to all the reinforcement end of chapter problems 1, 2, 3, and 4 so far. Yeah, so all of my live notes are just in the GitHub. I will also probably provide them in the Discord eventually when I get some more. Yeah, I'll probably post post the files in the Discord as well. So the Discord below has all of my study resources. Okay. All right, amortize analysis of dynamic arrays. In this section, we performed a detailed analysis of the running time of operations on dynamic arrays. We performed a detailed analysis. Okay, we use the big omega notation introduced in section 3.3.1, right? So remember that big O was worst case scenario for a function, whereas big omega is its best case scenario or its lower bound. to give an asymptotic lower bound on the running time of an algorithm or step within it. The strategy of replacing an array with a new larger array might at first seem slow because a single append operation may require omega n time in its best case scenario, right? To perform, where n is the current number of elements, so we can only run as fast as the number of elements provided. However, notice that by doubling the capacity during an array replacement, our new array allows us to add n new elements before that array must be replaced again. In this way, there are many simple append operations for each expensive one. This fact allows us to show that performing a series of operations on an initially empty dynamic array is efficient in terms of its total running time. Interesting. Using an algorithmic design pattern called amortization, we can show that performing a sequence of such append operations on a dynamic array is actually quite efficient. So we're trying to show that when we create a new array, it might seem slow, but we actually are having the ability to create that initial array, and then we can add items constantly to it. And we have an amortized time complexity because I think it's an overall sum. Like think of like an amortization schedule for like a car insurance or car payment, right? Or like a credit card or whatever, like interest payment. It's like a total sum of the various charges or whatever you're counting in this case. So if we have like a general sum of that we're kind of leaning towards, think of like almost like a bell curve. As you can see, we have a right skewed bell curve here showing you that I think, well, yeah, it's kind of got to get into that here. So using to perform an amortized analysis, we use an accounting technique. Yeah, so for those of you that don't know, my first year and a half of college, I was an accounting major. So I do know about this a little bit. Where we can view the computer as a coin-operated appliance that requires the payment of one cyber dollar for a constant amount of computing time. When an operation is executed, we have enough cyber dollars available in our current bank account to pay for that operation's running time. Thus, the total amount of cyber dollars spent for any computation will be proportional to the total time spent on that computation. Okay. The beauty of using this analysis method is that we can overcharge some operations in order to save up cyber dollars to pay for others. So prop 5. This is running times of a series of append operations of a dynamic array. So primitive operations for an append number of elements. So as you can see, we have these jumps when we have to create the new arrays, but in between here, we have constant time operations happening. So yes, when we have to create larger and larger arrays dynamically, which house x amount of space or 2x more space in the current length of the array, we have to, being shown by these are doubled, right? It does these jumps, but in between them we have these constant operations until we get that capacity limit. So prop 5.1, let S be a sequence implemented by means of dynamic array with initial capacity of 1. So we have some sequence S that's a dynamic array with a capacity of 1. Using the strategy of doubling the array when full, the total time to perform a series of n append operations in S starting from S being empty is O of n. So we're I don't know what the word, the agitation, I don't know, but we're proposing that that when we are appending the total time performed a series of n appending, right, we're doing n appends on S is O of n time, right? We have to append each element. Let us assume that one cyber dollar is enough to pay for the execution of each append operation in S, excluding the time spent for growing the array. Also, let us assume that growing the array from k to size 2k requires k cyber dollars for the time spent initializing the new array. We shall charge each append operation 3 cyber dollars. Thus, we overcharge each append operation that does not cause an overflow by 2 cyber dollars. Think of the 2 cyber dollars profited in an insertion that does not grow the array as being stored with the cell in the element was inserted. Okay, this is getting confusing quick here. Where'd you get the PDF from? Yeah, so this I just looked it up online. This is data structures and algorithms in Python. I just looked this up online, or I also have a saved copy provided in my Discord link down below. Um, Thus we overcharge. Okay, so also let us assume that growing the array from size k to doubling the array size requires the initial k cyberdollars, right? You have to add another k to it to get to 2k. So k plus k equals 2k, the new array, exactly. So it requires k cyberdollars. We shall charge each append operation 3 cyberdollars. Thus, we overcharge each append operation that does not cause an overflow by 2 cyberdollars. Think of the 2 cyberdollars profited in an insertion that does not grow the array as being stored in the cell in which the element was inserted. An overflow occurs when the array S has 2 to the power of I elements for some integer I is greater than 0. Okay. When the size of the array used by the array representing S is 2 to the power of I, okay, thus doubling the size of the array will require 2 to the power of I cyberdollars. Fortunately, we see these cyberdollars can be found stored in cells 2 to the I minus 1 through 2 to the I minus. Yeah, this is getting really jargony here. So this probably, honestly, this isn't really helping us too much here. Therefore, we have a valid amortization scheme in which the operation is charged 3 cyberdollars and all the computation time is paid for. That is, we can pay for the execution of n append operations using 3n cyberdollars. In other words, the amortized running time of each append operation is O of 1, hence the total running time of n append operations is O of n. So it's like, what I think it's getting at is it's trying to basically average out these costs. Like it's saying that if we are doubling the O of 1 constant time operations for each new array, well, these kind of cancel each other out in a sense, and the total running time of n operations is O of n. Because think of it, this kind of represents kind of like a linear curve when evened out, I bet you, across all elements. But it's this way of putting it is pretty confusing. I'm going to be honest. I didn't understand this whole thing of cyber dollars like at all. Figure 5.14, illustration of a series of append operations on a dynamic array. An 8-cell array is full. Okay, we have an 8-cell array which is full, with 2 cyberdollars stored at cells 4 through 7. So in cells 4, we have 2 cyberdollars, 2, 2, 2. Okay. B, an append operation causes an overflow and a doubling of capacity. Copying the 8 old elements of the new array is paid for by the cyberdollars already stored in the table. Inserting the new element is paid for by 1 cyberdollar charged to the current append operation, and the 2 cyberdollars profited stored in cells 8. Oh, okay. Yeah, that was a weird, I don't know about that. Airsick Titan, hey bud, hoping things are going well. Yeah, thanks so much for coming in. How you doing? Welcome, welcome. Welcome back. Okay, geometric increases in capacity. Although the proof of Prop 5.1 relies on the array being doubled each time we expand, the O of 1 amortized bound per operation can be proven for any geometrically increasing progression of array sizes. When choosing the geometric base, there exists a trade-off between runtime efficiency and memory usage. With a base of 2, doubling the array, if the last iteration causes a resize event, the array essentially ends up twice as large as it needs to be. If we instead increase the array only 25% of the current size, the geometric base of 1.25, we do not risk wasting as much memory in the end, but there will be more intermediate resize events along the way. Still, it is possible to prove an O of 1 amortization bound using a constant factor greater than 3 cyberdollars per operation used in the proof of 5.1. The key to the performance is that the amount of additional space is proportional to the current size of the array. Got you. Okay. So they're saying like you can use a base of 2 for your multiplying of the array, but if you were to just append only one, and your last operation was appending only one, and it caused you to go over and have to create a 2, well, you'd have a lot of memory space that's blank and being unused. So you could lower your geometric factor and lowering the risk, and you can still prove that O of 1 amortized bound, right? Doing good, doing well, taking a break from my own studying. Brain is toast, but all worth it in the end. Yeah, I'm feeling that for sure. Thank you for stopping in today. Okay, so beware of arithmetic progression. To avoid reserving too much space at once, it might be tempting to implement a dynamic array with a strategy in which a constant number of additional cells are reserved each time an array is resized. Unfortunately, the overall performance of such strategies is significantly worse. At an extreme, an increase of only one cell causes each append operation to resize the array. Right, an increase of only one cell causes each append to resize the array, leading to the familiar 1 plus 2 plus 3 all the way to n for O of n squared overall cost. Using increases of 2 or 3 at a time is slightly better as portrayed, but the overall cost remains quadratic. So if you had a step increase of 1, right, you'd have to increase the array at each step point, and then this would cause a summation and over omega n squared overall cost. We still have a quadratic with a step of 2 or 3, it says. So running times of a series of append operations on a dynamic array using arithmetic progressions of sizes. Assuming increase of 2 in size of the array, while B assumes an increased size of 3. Alright, using a fixed increment for each resize. And using a fixed increment for each array size and thus an arithmetic progression of intermediate array sizes results in an overall time that is quadratic in number of operations, as shown in the following proposition. Intuitively, even an increase in 1,000 cells per resize will become insignificant for large data sets. Performing a series of n append operations on initial empty dynamic array using a fixed increment with each resize takes omega n squared time. Okay, so we're going to justify this prop. So we let C be greater than 0, represent some fixed incrementing capacity that is used to resize each event. During the series of n append operations, each time will have been spent initializing an array of size C, 2C, 3C, all the way to MC, for m equals n divided by C, ceiling of that operation. And therefore, the overall time would be proportional to C plus 2C plus 3C all the way to m times C by prop 3.3. Oh, hold on, my girlfriend's here. All right. I'm about to start an analysis of algorithms course. How much math is involved? It's not too difficult. It was a little bit of a refresher of some of my, algebra courses, like relearning some of my exponent and log rules. But I haven't had to go do anything with like calculus or any of that so far. So I would just say maybe like pre-algebra is probably, or pre-calculus is probably the refresher you'll maybe need a little bit. But anything on that, like asymptotic analysis, asymptotes and stuff like that, yeah, that's all pre-algebra or pre-calculus. Sorry. So for all the values of for all the values of m, for I equals 1, we have some constant c equals I. Okay, cool. Therefore, performing the n append operations takes omega of n squared time. A lesson to be learned from Prop 5.1 and 5.2 is that a subtle difference in an algorithm's design can produce drastic differences in the asymptotic performance, and that a careful analysis can provide important insights into the design of a data structure. What's this?
My Ben's mom got it and gave it to me.
Oh, really?
Yeah. I didn't try it. It's like, I think it's just ham and cheese and lasagna or something.
Oh, thanks. Thank you. Okay. I got a sandwich. All right. So this is interesting. I'm gonna let's ask. Can you explain geometric increases in capacity in simple for algorithms in simple terms? Uh, a geometric increase in capacity refers to a situation where the size or capacity of something grows multiplicatively rather than additively. In the context of algorithms and data structures, this idea is often used to optimize how resources and memory or processing power are allocated. Using the here's a simple version. Imagine you have a bag that can hold items, but it's too small. If you double the bag size every time it runs out of room instead of adding just one more slot at the time, that's a geometric increase in capacity. The size of the bag grows by multiplying it by a constant factor like 2, rather than adding a fixed amount like 1 each time. Why is this useful? When an algorithm or data structure like a dynamic array grows geometrically, it has one, fewer expansions, we don't need to resize as much, and we have an amortized cost. Even though resizing takes some time, some effort, spreading this over all operations makes the average cost per operation low. Example of a dynamic array. We start. Okay, that made a lot more sense. Why didn't they just break it down like this? So we need to make a definition here for amortization, and then we'll say geometric increases in capacity. All right, so I'll get those notes in a second. Cool. Um, Interesting. Memory usage and shrinking an array. Another consequence of the rule of a geometric increasing capacity when appending into a dynamic array is that the final size of the array is guaranteed to be proportional to the overall number of elements. Another consequence of the rule of geometric increase is in a capacity when appending to dynamic arrays is that the final array size is guaranteed to be proportional to the overall number of elements. That is, the data structure uses O of n memory. This is a very desirable property for a data structure. If a container such as a Python list provides operations that cause removal of one or more elements, greater care must be taken to ensure that a dynamic array guarantees O of n memory usage. The risk is that repeated insertions may cause the underlying array to grow arbitrarily large, and that there will no longer be a proportional relationship between the number of elements and the array capacity after elements are removed. Okay, so if a container such a Python that provides operations that cause removal or one or more, greater care must be taken to the dynamic array. So if we're removing, we need to take greater care to have O of n time, because if we do too many insertions may cause the underlying to grow arbitrarily large. A robust implementation of such a data structure will shrink the underlying array on occasion while maintaining O of 1 amortized bound on the individual operations. However, care must be taken to ensure that the structure cannot rapidly oscillate between growing and shrinking the underlying array, in which case the amortized bound would not be achieved. In exercise C516, we explore a strategy in which the array capacity is halved whenever the number of actual elements falls below 1/4 of that capacity, thereby guaranteeing that the array capacity is at most 4 times the number of elements. We explore the amortized analysis of such strategies in exercise C517 and C518. Okay, that was a lot of information, but the gist of this was that when we need to be careful and take into account when we the constant factors that we're multiplying our array by when we're creating that new array size and resizing it, because too large of a constant factor and you create a lot of memory space that isn't being used, but too small, you're having to resize every single time. Whereas when you're shrinking the array, um, when you're shrinking the array, that's another. I'm a little bit more confused on the shrinking part, so we'll have to get some more practice with that. All right. Well, now we're on page 200, so I think this is a good place for us to pause for. Oh, one more page here. We'll do one more page before we get to 5.4. 5.3.3, Python's list class. The experiments of code fragment 5.1 and 5.2 at the beginning of section 5.3 provide empirical evidence that Python's list class is using a form of dynamic arrays for storage. Yet a careful examination of the intermediate array capacities suggests that Python is not using a pure geometric progression, nor it is using an arithmetic progression. With that said, it is clear that Python's implementation of the append method exhibits amortized constant time behavior. Yeah, so as remember from before, we looked at that chart that had those array sizes that were increasing based on the as we were appending elements into it, and they weren't going up evenly every single time, so that there was a factor being multiplied maybe onto our factor, increasing it for certain for as our n capacity reaches infinity, we probably really start to ramp up the increase. We can demonstrate this. Okay. We can demonstrate this fact experimentally. A single append operation typically executes so quickly that it would be difficult for us to actually measure the time elapsed at that granularity. Although we should notice some of the more expensive operations in which a resize is performed, we can get a more accurate measure of the amortized cost per operation by performing a series of n append operations on an initially empty list and determining the average cost of each. A function to perform the experiment is given in code fragment 5.4. So from time, we import time function from the time module. We define a function called compute average where we take in some value of n. So we perform n append, so the n is an integer that is the amount of appends we're going to perform in the list. And we're going to return the average time elapsed for all these appends. Okay, so we provide some average, we take a start time, we run the loop, append all of them, return append none into each place, and then return the time per n, so the average time per operation. Technically, the time elapsed between the start and end includes the time to manage the iteration of the for loop. Technically, the time elapsed between the start and end includes the time to manage the iteration of the for loop in addition to the append calls. The empirical result of the experiment for increasingly large values of n are shown in table 5.2. We see higher average cost for the smaller data sets, perhaps in part due to the overhead of the for loop range. There is also a natural variance in measuring the amortized costs in this way. Because of this impact, the final resize event relative to n. There is also a natural variance in measuring the amortized cost in this way because the impact of the final resize event relative to n. Taken as a whole, there seems clear evidence that the amortized time for each append is independent of n. So the average running times of the append measured in microseconds observed of the overall sequence of n calls. So as you can see, for these data sets, we don't even for these larger n values, we don't even really change much time, whereas we have significant time changes down low. It's probably being impacted by our for loop. So as you can see, the append method does not have like an asymptotic behavior associated with it. It has a constant behavior. Things are happening really, really fast. Chase, hey, thank you. I appreciate you coming in. No right way to long way to learn computer science. Awesome. Benjamin Scott, people seem to forget that you're not married to a programming language. Oh, you guys are telling yeah, yeah. Just whatever whatever Learning is it's your own time. This is your own time spent doing something. Hold on, let me back up. This is your own time spent doing something. So whatever it's your life, your time. So don't let people. There's obviously going to be somebody out there, people that are going to tell you you're wasting your time, but you know. I really don't think I am wasting my time because 6 months ago I didn't even know what a line of code was, and now we're learning about DSA, we're understanding it, we're processing it, and we're writing projects. Like we wrote our small business manager project that we're writing. We have all of these, functions that we've written here for, these are smaller functions that don't really have much meaning, but we have larger functions here for file writing that we've written by hand, like all on our own. We have we have a create menu function that we wrote to dynamically create menus because we noticed that we were creating menus over and over again. We have object oriented classes that we're using. We're importing dates, managing third party modules. So we're just little by little. Rome is not built in a day, you guys, just as that cliche says. So but I appreciate you guys all being here and supporting the channel. Thank you guys so much. So yeah, this is proof that those append operations are happening in O of 1 time, constant time, because we are shown that the time isn't really changing as our n inputs grow extremely large. Shoot, got way lost here. Right, so this was that example I wanted to show you guys. As you can see, there isn't a constant factor being increased. It is dynamically increasing in its own way, probably having some initial factor, and then as we maybe check for larger ends, we increase, we factor on that factor as well. So it might become even more layered. Thank you so much for all you do in streaming. Cheers. Yes, I'm really glad that you guys are enjoying this and this is really working out for the stream. This was my goal all along, is to provide a beginner's perspective. I found that the creators and videos that I was watching online didn't really have, it was all people that were super advanced trying to convey the information from an advanced person's point of view. And it felt a little bit of detached and disconnected from the reality that, man, this stuff is really hard. And when you first see this for the first time, I think they might be a little out of touch at what it was like for them that first time. So I wanted to provide a raw beginner's point of view, just grinding through this word line by line, concept by concept, what it kind of realistically would look like for a normal person to try to pick this up on their own. So I really enjoy that you guys are getting what I am desiring out of this. And yes, thank you guys so much for joining me here. So I'm going to stop here on DSA in Python 5.4, page 202. This looks like a good place to stop for right now. So we got a lot of good notes here so far. I do need to go back through and polish things up a little bit, add a couple notes for these sections that were a little bit vague. But I am going to, I want to jump to the small business manager really fast and show you guys what we got going on so far. And then I think I might call it a night from there. And then we'll be back tomorrow. And then we will obviously be doing a lot this weekend as well. So in our main function here, we have successfully actually managed to add refactor our code to access items in constant time now, rather than having to do binary search. So in the book we were just reading, we learned about binary search, and we actually a few streams ago wrote a binary search function to actually accessing items in our database. Now we found that that wasn't the best way to do things, because we were having classes and child classes and child classes of that child, and so we decided to refactor things and place these attributes within just a single item class and manage it on a singular level. So let me just demonstrate what we got so far. So this is the small business manager. If I press 1 to enter the program, we just enter in, and so we're prompted with these two options we have so far. We're going to obviously expand from here, but we have the inventory menu, we have the transactions menu. So we've only been working on the inventory menu for now. If we press the inventory menu, we can add an item or we can find and edit items. So we have the add item completely implemented. So we can add an item. Let's say this is stream item. We have a 10 for a cost here. We have an item size of a medium. And today's date, yeah, let's go ahead and use today's date as our creation date. And let's say we have 3 of these items. So if I go ahead and exit out of my program, as you can see, those items were just generated and saved into our item CSV file. And so these items are active by default and have these other placeholders for these data points for when they get transitioned into for sale for a date listed and a listing price, and obviously for a when they transition to a sold transaction for a date sold and a sold price. So we're going to successfully be able to manage and alter these attributes in constant time and override them when we want to actually transfer these items into those different transitionary phases of its life cycle. So that being said, we also added an ability to be able to just directly access individual items to hopefully edit them. So if we go back to the inventory manager of the menu and then press find and edit, we can if we press 1 to do it by item number, that's all we have implemented so far. We can just say let's just do 100 and see what it says, right? If we enter 100, we get this error, item number 100 not found. So we immediately do a check if it's within our bounds of our item numbers, the length of our keys in our dictionary, because that's what's housing our item numbers is the keys. So if I just give like a 10 here where we do have an item number, or we don't have an item 10, let's see, we have an item number 8 is our max number. So 8, boom. Right now we're just retrieving that item and we're showing that the item is being successfully detected in our file and retrieved. So you can see that all of that is consistent with this item here. So we can actually now, edit individual parameters in case we made a mistake when we uploaded the item, the user did, or we could even at this point, run a transaction, transact this item or something, right? So, and then that would take us to our transaction menu. So it's just, we can go a lot of different ways from here. We do have a lot to implement and not a lot of time on the daily, so it is quite a slow process, little by little, but over the course of a few weeks, we've come pretty far in creating some process here. So it's been great, and yeah. So Jordan Woods says, "Hey, how are you? Thanks so much for coming in. I appreciate you joining me tonight. Um, if you guys are enjoying the stream, make sure to, if you guys would feel so inclined to follow along to the channel, maybe throw it a thumbs up or something, and just helps to keep me motivated. And obviously, I keep coming back every day and wanting to learn this stuff. The stream definitely helps too, when I know I can come back and talk to you guys here. So right now we don't have any way of actually exiting out of the item number creation menu. So that would probably be our next place to actually, edit to implement that. So is this project on your GitHub too? No, this project isn't on my GitHub. I've had a lot of requests though to push it to my GitHub sooner rather than later so people can follow along. This project is pretty similar in structure so far to the task tracker that is pushed to my GitHub right now. So that project is completely incomplete. So if you want to reference that, feel free. That's currently pushed, but I will be pushing this soon. I wanted to just get a few more features added so I can have something at least working, but people have shown a lot of interest in actually just wanting to follow along in their own right and see the changes I've made from their end and through through what Git does. So yeah, I'll probably do that this weekend. So in our find run edit item, we create the menu for item number name, right, which is this menu that's created. If we press 1, we ask for the item number. So we need to allow the user to quit this at any time. So we need to say, um, um, so this gets us into we need like a go back, right? So we need an option here for um, hmm, So how should we do this? So we're not creating a menu here. So we have the user input that's being created, and so we're detecting that user input here. So if I want to provide a user to quit, I need to print a statement or have a user also take in another input. But if user input is Q, elif user input is equal to quote, we'll say Q, we want to, so here we will say item number, and then we'll just have a print statement here for press quote Q, or enter Q to go back, right? So we'll say Q here, enter Q to go back. If user input is equal to Q, we want to just run the run add item function again. So that'll just take us back to our previous, no, not run add, yeah, run add item function, which is, no, not run add item, which is find search. So we need to go to run inventory. That's what we were called from, right? So now let's go ahead and see what that does. If we run this, go yes, inventory, find edit, item number. Okay, we're not getting that print statement. What happens if I press Q? I don't get it. We get this value error. Because we're trying to detect this integer here. So should we create a menu here then? No, we don't want to create a menu. We want to ask the user for user input. How do I want to do this? So the user will enter an input, we convert that to an integer, at least we try to. If it's not, if we get a value error, we say please enter an integer and number. So we can't provide Q here because we're inputting, because user input is automatically being converted. So now we're getting the enter, please enter. Okay, so that's why this isn't showing, because it's not detecting that. So we need to get rid of that. We need to say if user input not, we'll get rid of this. Except for a value error, we'll continue the prompt. We'll ask for a user input here. No, we don't want to ask for user input here. So we have the item, we found it. If the item's not found, do we want to continue the loop, or do we want to just go back? We don't provide the user with an ability to exit out of this at any point. So they have to edit an item over here. So we're going to get a user input. In my try statement, this is what we're going to do actually. Oh, this is what we'll do, I think. I'm going to get my user input outside of my try statement. Inside of my try statement, I'm going to convert user input to an integer. User input equals int user input. We're going to convert user input to an integer and then try it, right? Okay, then before we get into our try loop, we're going to say if user input is equal to quote q, we will print, we'll call run inventory, right? Else we're going to try and do that. Okay, perfect. So that should take care of that. So if they enter Q, but we need to ask for them for a prompt. So ask for user input here. So we're waiting at this point. And then I'm going to also, can I like, we're waiting for input at this point, so it's not going to print anything. We need to have a display here. We need to have like a print above here that says press quote Q to quit to go back, right? And then we're going to make this a new line. So now if we run this, we get this. Inventory, find, edit, we get item number. Okay, we get press Q to go back. So I want to, if I run item number, we want to here in the while true, we want to clear terminal here, right? So now if I run the program, inventory, find, edit, item number, we get, now it clears. We get press Q to go back or item number. So if I press Q, we go back to the main menu, we can press go back to item number, we go item number. To go back to inventory menu. Okay, so now if we run, go yes, inventory, find, edit by item number, now we get this. Press Q to go back to inventory, item number. So now if we could press 4 here, we get it, right? So we're still getting that item, it's just continuing the loop just based off this nature. It's because we don't have anything here yet. So now we need to do like an edit item function where we'll prompt the user to be able to actually edit the individual parameters of the item. So cool. We'll work on that tomorrow. I appreciate you guys joining me. This one was a little bit shorter, or not a little bit shorter. We streamed for 2 hours. We did about an hour and 20 minutes, hour and a half on DSA and Python, learning about chapter 5, about data structures and arrays, lists, tuples, stirs, all that kind of stuff, managing memory allocation on data, and associating how to manage the memory time complexities associated with that, which was really interesting. So we're going to continue chapter 5 tomorrow, and then we spent about 15-20 minutes just adding in a little bit of a feature here on our project here. I do want to consider ways and think of ways to actually clean up our program. It's getting a little bit chaotic here, and I'm starting to get a little bit overwhelmed with the amount of functions, and it's just hard to kind of map everything out. So we might need to figure out a way of organizing things. But again, guys, I am a beginner. I teach myself Python every day, or various computer science concepts. I have a Bachelor of Science in Human Biology, a minor in chemistry, and I stream, I try to my best Monday through Friday from about 7 p.m. PST to about 9:30, sometimes even 10:30, or maybe even 11 sometimes, when I'm really in the mood and feeling like continuing. But I'm gonna take a break here and spend some time with my girlfriend and watch a show before going to bed. And I got a 9 to 5 tomorrow anyway. I'm a chemist, for those that don't know. So yeah. Anyways, I'll be back tomorrow. Thanks so much for the support, guys. Please follow along to the stream if you're wanting to stay connected, and join the Discord link below to gain access to all my study resources. I really, really enjoy talking to you guys, and this stream makes learning this stuff so much more enjoyable. Even though I really enjoy doing it anyways. Again, I'll see you guys tomorrow. Thanks so much for being here. Yeah, bye guys. Oh, thanks for 500 subs too, by the way. Woo!